Hello, today I'll be talking about the Newsvendor problem, which is the most fundamental probabilistic model for dealing with demand and inventory quantity. So in Newsvendor, you assume that you're starting with zero inventory and you're deciding how much to produce based on the demand and associated costs of, right? So your decision is going to be Q, which is the initial inventory chosen by you, right? And then we'll say Q star is the optimal Q. So the Q star that produces the most profit. And we have to know some information about the environment we're selling in, right? So D is going to be our random variable for the demand. It gives us probability distribution of different values for the demand. CP is the unit purchase or production cost. So if you're buying from a distributor, that's how much you buy it for, or if you're making it yourself, that's how much it costs to make a single unit. And then we have CH, which is the unit holding cost. And so these notations are very different. Like many places don't have Q, they have Y or I or whatever. But like what's important is the meaning is always the same in the Newsvendor problem, right? So holding cost is when you have more units than the demand, there's some leftover units and you have to hold on to them to the next period. So like holding cost is cost you incur when you're not able to sell everything. And it's per inventory unit left over, right? And then we also have P, which is the sales price. So for each unit that is sold, you're going to gain P dollars in revenue. And we can also say B is CB is the unit back order cost. So this is saying when the demand is greater than our inventory on hand, we have to do a back order. Like we incur some loss because the demand was not fulfilled. Many stores, that loss would be zero. You just don't have that sale. But sometimes, like you would give some compensation to the customer, especially in a big business factory setting, right? And so our objective is how we're going to decide this decision Q, our decision variable. So our objective is to maximize profit, which equals revenue minus cost. And like specifically, we can break cost into the different components. So equals revenue minus purchase / production cost minus the holding cost minus the back order cost, right? And so let's call this a function for profit pi of d comma q. So d is an input to the function. Of course, these are all inputs as well, but these are like parameters that are going to be non-random, and versus d is a random variable. And then q is our decision variable, so it's what's we're choosing, right? And so let's write our expression for profit is going to be P, the sales price, times the number of units sold. Let's just leave it like that for now. Right? So we have really two cases where the number sold differs, right? If D is less than Q, that means the demand is less than the initial inventory on hand, right? So how many are we going to sell? That's simply D. However many customer requests come, we're able to fulfill all of them. So our sales is the number of customer requests, right? The other case is when D is greater than Q. And in the discrete case, like there is the D equal to Q case. But really, that's not important to distinguish which one, because then like the cases are going to be equivalent. So this would be the same as if we had a less than or equal to sign, but yeah, let's just say D strictly greater than Q. That means we have more customers than inventory. So how much we're able to sell is simply our inventory. So our expression for this number of units sold, right? So we're going to have the P out front still, and we're saying if D is less than Q, then we sell D. If D is greater than Q, then we sell Q. So the number sold is the minimum of D and Q. And then for purchase cost, we have this unit purchase production cost. And then we're going to have the number of units produced or purchased, which is simply like how much initial inventory we're going to make, right? So it's minus CP times Q. And then the CH is our unit cost. And then we have the number, I'm going to say overstocked. So that I just mean the number of units that are not sold. So if D is less than Q, we've satisfied all the customers. We have more inventory than demand. So there's no overstock, right? But wait, D less than Q. No, that's when we do have overstock. Sorry. Well, I mean, you should be thinking about it yourself, right? When we have more inventory on hand, that means there's going to be some left over. So Q minus D is our number overstocked. And in this other case, that's when we have zero overstocked. There's more demand than we were able to fulfill, right? And then the back order is going to be CB, the unit back order cost, times the number understocked. So that by that I mean the number of units that customers requested, but we were unable to fulfill, and we paid this back order cost, right? So when D is less than Q, that's zero. We were able to fulfill all the demand. Here, it's the difference between demand and quantity. However many units we were not able to provide that the customer demanded, right? So we'll put these, carry this down, right? Minus CH, and then like, so this, we want a single expression that combines both of those. It's simply the maximum, right? Because if this is the case, if this is not the case, then this is negative and our maximum is zero. So this is maximum 0 Q minus D. We also denote that as Q minus D positive sometimes. I'm probably going to just leave it as max 0 Q minus D in case you're not familiar with that notation. And then we also have minus CB times the number understocked, which is also going to be the maximum of these two. Because when we have 0 understocked, then D minus Q is negative, and the max is 0, D minus Q comes out to 0. Right? And so this is a little bit of a complicated function because of this thing. We have minimum of D and Q, so a random variable and a constant that's could be less than Q or could be greater than Q. I mean, Q could be greater than D or less. So like this thing is a little difficult, right? So instead of phrasing it in terms of profit, let's phrase it in terms of cost, right? So let's make a new function, C of dq equals the purchase production cost plus the holding cost plus, now we're going to say the shortage cost. So this shortage cost is the back order cost, like this extra cost we incur for not being able to fulfill the demand, and the lost revenue. So instead of calculating the entire revenue, let's just calculate how many customers came that we were not able to fulfill, and add that to our cost, because that's losing out on revenue, that's decreasing our profit, right? So really, lost customers can be represented as a cost instead of negative profit. So backorder cost plus lost customers, which means like we're simply going to be adding P to this CB, right? So let's say CS is the unit shortage cost, and so for every customer missed, we um, lose out on the revenue P, and we pay the extra cost CB. Maybe CB is negative if they're able to buy something else, etc. Like holding costs could also be negative if we were able to like salvage the product and resell it at a discount or whatever. Um, yeah, and from here, like this is going to get us an easier expression, because now like the shortage cost is this unit shortage cost times this number understocked. So we've gotten rid of this and kind of merged it over here. So this is going to be the same, CPQ plus holding cost is going to be CH times maximum 0Q minus D. And then we're going to have CS as our unit shortage cost times maximum 0 D minus Q. Yeah, and that's our cost function. And as I was explaining throughout, like both of these are going to have the same corresponding maximum Q. They're not going to have the same value because this one doesn't include the revenue, right? And that one we actually want to minimize because we want lower cost versus profit. We want higher profit. But as I said, like it's going to give us the same Q that we want. So the argmax over Q pi of dq, that means the Q that maximizes profit equals the Q that minimizes C of dq, as I just explained. And that gives us a much simpler expression, C of dq, that we can optimize, find Q star. Because that, yeah, the purpose is to decide Q. And we want it to be Q star, the optimal one, right? And then, but I mean, in some cases, we still want to know how can we calculate pi. Like if we said C of dq equals 10, what is pi? Like because knowing what the profit is important, right? So let's quickly relate those two functions. Like as I was doing, like P of dq equals the revenue not counting the like lot potential for lost customers, right? So it's simply just the price times the demand, where because this shortage cost now has the lost customers accounted for, and then minus C of dq. Versus before, our revenue was P times minimum dq. Now, like the minimum D minus Q0 or maximum D minus Q0 is over there, right? So might be hard to see immediately why this is true, but if you like break it back into these sort of terms, then it should be intuitive. Yeah, but as I said, pi is not how we're going to find the maximum. How we're going to find the maximum is from C of dq. And so we need to have d fully defined. It's a assumption of the model. Let's say that it's a discrete distribution, discrete demand, because that makes sense, because for many cases, like we have quantity is a number of units, like we have exactly 10 books we're selling, or in the newsstand 10 newspapers, and people can buy exactly one or two, etc. Right? So we have a PMF that gives us the probability d equals a value x equals f of x, right? So PMF is just a function. We input the value, it gives us the probability of that value, right? Sometimes it's called P of x or P subscript x, whatever, or you can just leave it as probability d equals x. But I'm going to use f of x notation, and then we want to find the, well, wait, let's explain why this is the case. So let's think about how we're going to find q star. We have our C of dq. Well, C of dq is random. It depends on what d is. But we could find the q that minimizes the expected value of CQ. That will have a minimum. And so this is going to be a concave function, something like this, right? We have exactly one turning point, one minima, and this is our Q star. So Q star is the last Q with decreasing cost. Like Q star last Q with decreasing cost, or in other words, we can say the minimum Q such that the expected value C d Q plus 1 minus the expected value of C dq is greater than 0, right? If we look at the cost of Q plus 1, it's greater than the cost of Q. Yeah, and so that's how we're going to define our Q star. We're going to minimize this, but then we can simplify this, right, to get a nicer expression, because we have this equation for C. So if we look at taking this C of dq, let's just rewrite it. C of dq equals CPQ plus CH max 0 Q minus D plus CS max 0 D minus Q. Yeah, perhaps I even should have done this before moving on. Like this maximum, we want to write in terms of this PMF, right? So we have the distribution of D fully defined. So CPQ and then CH times when is the demand going to have Q minus D greater than 0? Well, as we already talked about, it's up here in this table. We have when D is less than Q, we are paying this holding cost, right? So we can sum, since we're in the discrete case, we're summing over the X, since X is like our input to the demand function. We're summing over the X from 0 to Q. So that covers all the X that are less than Q. We're going to incur, what is the number that is going to be overstocked? It's not X, it's Q minus X, right? Q minus D. And now X is our specific value for a random variable D, right? So Q minus D is the number understocked, and then we want to multiply it by that probability, f of x. And then for CS, we're going to do the maximum of D minus Q. So in terms of what values of demand do we incur the shortage cost, it's when D is greater than Q and our value is X minus Q, right? So we're going to sum over the X that are greater than Q. Since it's discrete, the next one after Q is Q plus 1, and then we go up to infinity of, and dx minus q, or d minus q, is our number of shortage, and then we multiply it by that probability, right? Because the expected value is the value times the probability summed up over all the values. C of dq. And then now we're looking at the difference in E of C dq plus 1 minus E of, sorry, here I need to write the expected value, right? Because I went from, this is just the random variable generally, this is the expected value of the random variable. C D Q is like, we're going to take this function, plug in Q plus 1, subtract the Q. Q plus 1 minus Q plus CH, right? Sum x equals 0 to Q plus 1 is when we plug in Q plus 1. Q plus 1 minus x, f of x. Subtract when we plug in q, sum from x equals 0 to q, q minus x, f of x. And that's all multiplied to the holding cost at the end. Let's zoom out a little. Sorry if it's a little small. Or let's just go to the right. Then the unit shortage cost, we're multiplying it by this thing, plugging in q plus 1 for q, and then plugging in q for q. So we have x equals q plus 2 to infinity, x minus q plus 1, f of x minus the sum x equals q plus 1 to infinity of x minus q, f of x, right? And so then this whole thing, what does this come out to? Look, these are almost the same, right? The difference is we have a q plus 1 up top instead of a q up top, and we have the 1 here and no 1 here, right? So like if you think about factoring and doing out your expression, right? When you plug in q plus 1, that actually comes out to 0, right? So like our difference is just going to be that 1 times f of x summed over x equals 0 to q, right? So we get, well, first of all, q plus 1 minus q is just 1. So we have cp plus ch times, as I was saying, the summation from x equals 0 to q times 1 times f of x. And then over here, it's the same sort of thing, except now the 1 is over here and we're multiplying a negative to it, right? So it's like we have negative sum x equals q plus 1 to infinity times f of x, or minus cs. When we're doing cs times this negative thing. So it's the same as minus cs times it. Minus cs x equals q plus 1 to infinity f of x, right? And this is cp plus ch. Now let's convert it back into probabilities to make remembering it a little easier. Yeah, so this is, we're summing over the PMF the values less than q, so that's the probability d is less than or equal to q. Well, I mean, we're also plugging in q, right? So probability d less than or equal to q. And then minus cs, this is 1 minus that probability, or the probability D is greater than Q, but let's leave it as 1 minus probability D less than or equal to Q. And then what were we doing with this expression? We were setting it greater than or equal to 0. So now let's set this greater than or equal to 0 and simplify. Cp plus Ch probability D greater than Q minus Cs 1 minus probability D less than or equal to Q greater than or equal to 0. If you do the algebra, it's going to come out to probability D less than or equal to Q equals Cs minus Ch Cp over Cs plus Ch. And that's the important result, right? So Q star is the minimum Q such that, sorry, this one's less than or equal to sign, so that shouldn't be equal sign, it should be greater than or equal to sign. And this probability D less than or equal to Q is called the CDF, also denoted as capital F of Q, right? So greater than or equal to this. And this is called the Newsvendor critical ratio. And sometimes we express it in terms of an inverse CDF, which just means you apply the inverse to both sides, then you're left with just Q on the left. But in the discrete case, it's easier to think about it graphically. We're going to look at the CDF. So it's a non-decreasing step function. Before some value, we have probability 0. And then after we hit the discrete values that have positive probabilities, we jump up a step. And then eventually we're going to hit probability 1, right? And so the critical ratio is some value between 0 and 1. Let's put it on the y-axis that we're going to compare to f of q, right? So critical ratio here, we want the minimum q such that f of q is greater than this critical value. So it's right here, is we're going to have q such that the f of q is greater than the critical value. So that's going to be our q star. And then let's jump down a second to where I've written an example. You run a food truck that sells burgers in a football stadium. The ingredients for a burger are purchased from a grocery store at $4 per burger, and your employee makes burgers quickly for a labor cost of $1 per burger. So already we see we're given just information about some scenario. We're trying to find Q star. And so we're going to expression in terms of these unit costs that we've defined up above. CP is the unit purchase or production cost, CH is the unit holding cost, P is the sales price, CB is the unit backorder cost, and CS is P plus CB, right? So we're just showing you an example. Like in the real world, you're probably not going to be told explicitly this is the backorder cost. You just in the context of the scenario, you have to decide which one's the backorder cost. So reading a word problem is not too difficult, right? The ingredients and the labor both go into the cost of producing a unit, right? So we have CP equals 4 plus 1 equals 5. And then we have each burger sells for $10 during the game. So that would be P equals 10. During the regular period, we're selling it for $10. After the game, you can easily sell all the remaining cooked burgers for $3. If you run out of burgers, you will give each remaining customer a free soda as an apology for the cost of $1. So this $1 is, we're incurring it when we have an understock. We have a shortage of items, and so we're paying this cost of $1. So we called that B up above, right? And then our CS, our unit shortage cost, was P plus B equals 11. And then what is this $3? Well, you get $3 at the end for every unit left over. So that's the overstock case. We made more than we were able to sell, but instead of incurring a cost, you're actually gaining a revenue. So we have a negative cost, negative holding cost. So CH equals -3, right? That's also called salvage value, whatever, fire sale. And so given these unit costs, we can compute the critical ratio using the formula up above, right? So CS minus CP over CS plus CH equals 11 minus 10 over, 11 minus 5 over 11 minus 3 equals 6 over 8 equals 3 over 4 equals 0.75, so that perhaps we could more easily compare it to the FCDF, right? And so then the second sentence, the quantity of burgers requested during a game is assumed to be between 20 and 30 with equal probability for each quantity. So that means we're given the distribution of D, the demand. It's going to be uniform between 20 and 30, and by that I mean discrete uniform. We have 21, 22, etc. burgers sold, a round number, right? And so let's write f of x, the probability of selling f burgers, or PMF, right? So that's going to be, we have 11 different quantities we could sell, 20, 21, all the way to 30. So the probability of each is equal. So it's 1 over 11. And that's for x is in 20, 21, 30, and that's 0 otherwise for x not in that set. And then, so how we found the Q star was we want the minimum Q such that f of Q is greater than or equal to CS minus CP over CS plus CH, right? So this equals 0.75. We want to find the point that we're just greater than 0.75, right? So if thinking about the graph again, like it's pretty similar. We're gonna just have 11 steps. Pretend that's 11. I wasn't really counting. And we're gonna compare 0.75. We want to find the one that's just above. We want to find the Q that has a CDF just above 0.75. Okay, I cut out for a second for 8 over 11 and 9 over 11 because I wasn't remembering those fractions. If I had chosen a different number of points, then we would have had an easier fraction to deal with. But anyways, 8 over 11 is going to be the one just under 0.75, and then 9 over 11 is the one just over 0.75. So we're looking for the Q such that f of Q equals 9 over 11, right? And f of x is the probability demand less than or equal to x equals the sum over x equals 0 to x of f of x, right? We're just summing with how many we've passed, right? So to be at 9 over 11, we're at the 9th point out of the 11, right? So the 9th point is 28 because the first is 20. Or if we were writing the f of x as a clean function, we'd say it's 0 if x is less than 20, probability of being less than 20 is 0. Probability of being less than 30 is 1, so after 30 it becomes 1, right? And before then, we're going to take our number x, and since I'm writing a continuous range here, let's go ahead and write the floor. That means the lowest integer less than x. I mean, the greatest integer less than x, rounding down to the nearest smallest integer, right? And so we want to be able to plug in 20 and get 1. So let's subtract 20 and add 1. And then when we plug in 30, we'd get 30 minus 20 plus 1. That gives us 11, divided by 11. If so, long story short, we have f of 28 equals 9 over 11. So q star equals 28. And that's the example of Newsvendor. So really it's just reading comprehension and then learning how to find this inverse CDF for a discrete CDF. For a continuous CDF, it's a little easier because instead of greater than or equal to, we have equal to. All right, moving on. Now let's consider changing our Newsvendor model. We have to consider the inventory on hand. So we're starting with some inventory instead of starting with 0. Let's call that I and V. And we have a fixed cost of purchasing producing, operating, etc. Like when we purchase, well, yeah, maybe let's not include operating because so this is saying if we decide to keep our inventory on hand, not make any more, then we don't have to pay this fixed cost. Maybe it's the fixed cost of driving the truck or keeping the factory open, electricity and such, right? So this let's call CF. We only pay this fixed cost when we're ordering. So now, because of this CF, we're not always going to order up to Q star, right? If we're very close to Q star, let's say Q star was 50 units and our inventory on hand was 49, it wouldn't be worth paying this fixed cost to order one more unit, right? So in addition to Q star, we have a new threshold that's going to be when do we want to order, right? And we call this an SS policy. We want to decide the SS policy. So if the inventory is less than or equal to S, then we order up to S. Meaning we, instead of starting with I and V inventory, we start with S and we pay this fixed cost and the cost of ordering or producing or purchasing whatever the units. And this S is Q star from Newsvendor that we learned up above. And so then we would be going into the next period starting with S inventory on hand. If our inventory is greater than little s, then we're not going to order because it's more cost efficient to just start the next period with S on hand, like S in our inventory, S quantity available to be sold. And so this seems like a pretty good thing to add to the model. We do want to consider the case, what if we're not at S star? And there is pretty much always going to be some fixed cost of getting new units, right? And now we want to find out what this little s is, right? The big S is Q star. Little s, we have to compare the cost of ordering and not ordering, right? So maybe I've been doing graphically, we look at different starting inventories and different costs. Our cost of not ordering could be some function like this that's decreasing as we have more inventory. Once we're close to Q star inventory, our cost of not ordering is not very high. If we had 49 inventory, we wouldn't want to order, right? And then the cost of ordering is the opposite. If we started with 0 on hand, we would definitely want to order. But then there's going to be this intersection point S. That's our turning point. And that's where the cost of ordering equals the cost of not ordering, right? And that's the little s that we want to find. The point where we're deciding whether to order, right? So cost of ordering, or let's say not ordering on the left. Cost of not ordering equals cost of ordering. And really, I'm talking about expected cost because our objective was to maximize expected profit, i.e. minimize expected cost. So we're going to do C of, so if we're not ordering, we're still going to experience demand D, and then the quantity we're going to start with is S, little s, right? Over here, cost of ordering, we're going to have to start with big S on hand instead of little s. And this C function already includes the purchase cost, right? So this is going to incorporate this purchase cost being higher over here, right? And then we also have to pay the fixed cost of ordering in the case that we order, right? So our two options are start with little s, don't pay the fixed cost, or start with big S and pay the fixed cost. And let's recall our cost function up here, right? But we can go ahead and use the version where we've plugged in the f of x PMF, right? So we're just copying this guy. And instead of Q, we have S. So CPS plus CH times the number of units number of units overstocked, right? So we're summing from x equals 0 to S minus x f of x. And then we have CS x equals S plus 1 to, and I mean up here we could do S minus 1 because when you plug in S it's 0. And up here we could also just do S because when you plug in S it's 0. But again, like I'll write it in this form because that's how I wrote it up above. To infinity of the f of x, right? So expected value, we're taking the value overstocked times the probability that's the value overstocked. And then on the right side, we have the same thing, but with big S. And then we have to add the fixed cost. And there's no shortcut from here. To find this little s, we're going to have to plug in the specific values of x that are possible, the specific values of s that are possible. X, yeah. And find the resulting value of little s. Big S, we will have already have calculated from Newsvendor, right? So S is the Q star from Newsvendor. So we're going to have to substitute in that, and like this right side, we are just computing to a constant. This side is going to be a function of little s, and we have to solve for little s. Another way you could do it is just like compute this one and then start computing basically compute C of D comma Q for all the Q between 0 and big S and find which one equals big S plus the fixed cost, right? That's just going to be some computation, but all of these, like you could, with a small PDF, we could do that by hand, right? Let's go ahead and say, for example, our demand follows the distribution f of x equals, or maybe we just write it in terms of the random variable. I haven't done that in this video. Demand equals 10 with probability 1/2, 15 with probability 1/3, and 20 with probability, well, let's say it goes up to 30 with probability 1/6, just so that we get something divisible, right? That's the same as saying f of x equals 1/2, x equals 10, and then 1/3 for x equals 15, 1/6 for x equals 30, and 0 otherwise for x is not in 10, 15, 30. And then let's practice computing Q star. Let's say that our critical ratio was the same as up above. We have that's 0.75, right? So our critical ratio equals 0.75, right? If we look at f of x, when we have x less than 15, we would have 0, right? For 15 less than x less than, not 15, 10 is our first value. 10, we would have 0. For 10 less than equal to x less than 15, we'll jump up to 1/2. And then after the 15, we'll have added in this 1/3 probability, so we get 5, 6. And then at 30, we'll have added in the 1/6 probability and get up to 1, right? So 5, 6, is that greater than or less than 0.75? It's greater than. So f of 10 equals 1/2, and then f of 15 equals 5/6, which is greater than 0.75. So that's the Q star that we want. And now to find the little s, we're going to have to plug in this big S up here, and then leave the little s down there and solve for it, right? So let's take these values up from above. 5, -3, 11. So CP equals 5, CH equals -3, CS equals 11. Let's start with this equation up here, right? So we have CP is 5 times little s plus CH is -3 times summation from 0 to little s, right? So this depends on what little s is, but really we just have the values 10, 15, 30, right? So instead of like writing it, we could write it in terms of little s, and then we'd still have this whole expression the same. Let's go ahead and find the right side first. So we have 5 times big S, which is 15, plus -3 times the summation from 0 to big S, which is 15, of s minus x f of x. So basically, this is just our number of units understocked, overstocked, and then our number of units understocked, right? So each of these values has probability given, right? So if we made like a table, D is 15, 10, or 30, then our number overstocked here, our S equals 15, right? So our number overstocked is D minus S, positive, right? So here we're not going to have overstock. Here we're going to have, overstocked is S minus D, positive, right? How much we have left at the end. And then number understocked is how much we came short, how much demand we were unable to fulfill. So in these two cases, we fulfilled all the demand. In this one, we had 15 unfulfilled, right? So we're all the values from 0 to big S, really there's just 3 values where this f of x is a positive probability, right? So that's what we care about. Minus 3 times the one case we have overstock, we would be overstocked by 5 units with the probability that D equals 10, which is 1/2. And then we have CS is 11 times the number we would be understocked times the probability that we're understocked, which is 1/6, right? Or maybe we make another column for probability, 1/2, 1/3, 1/6. And then we have our fixed cost would be a new value that hasn't been discussed yet. Let's say it is 100, then we would just add 100 here, and we would compute this out. 4.5 times 15. Oh yeah, that's not clean. Like you can get a value for that, and then like over here, we'll have to consider S to be 10, S to be 15, S to be 30. Well, already little s is, or sorry, no, s is going to be something between 0 and 15. And we'll plug in like the possibilities, right? So on this left side, we have still CP times S plus CH times the number understocked, number overstocked. So the overstocked is just going to be, when we're less than 15, we have this 1/2 probability, and the number we're overstocked is S minus 10, right? Basically, we have the overstock case when demand equals 10. We have probability 1/2 of that, and the number overstocked is S minus 10. So our expected value is S minus 10 times 1/2. If that's a little confusing, we can just start from that, or like even remembering it, like going back to the last form could be just as helpful, right? This form, right? So we would have CH times the expected value of max 0 Q minus D. And now we have big S instead of Q, right? So max expected value, max 0 Q minus D. Perhaps that is easier to see how that comes out to S minus 10 times 1/2. Like make a table. Like we can label this max 0 and 15 minus D. And then this one would be max 0 D minus 15. And that's a little more clear to see that this is 5 times 1/2 and then 15 times 1/6. And then plus 11 times the overstock case, we have 30 minus S. And the probability of that is 1/6, right? So we want this left side to equal the right side. And that's just going to take some algebra, because right now it's a linear function in terms of s. Yeah, and then after that example, let's talk about what happens if we have a continuous demand function, demand random variable D, with a probability density function PDF, right? Then, our cost function CDQ equals CPQ plus CH, expected value of max, or if I'm writing the expected value, max 0, and then Q minus D plus CS, expected value of max 0 D minus Q. But in the discrete case, we said this expected value came out to summation from x equals 0 to Q of Q minus D, right? Yeah, Q minus X, F of X. I have to always double check because understock, overstock, it's really easy to flip these two units costs if you're not keeping track of which is which. And then this, we said, was the summation from x equals q plus 1 to infinity of x minus q f of x. And now in the continuous case, everything stays the same, except instead of a summation, we have an integral. So we have the integral from 0 to q of q minus x f of x dx for this term. And then this term, we're going to have integral from q to infinity. I started at q plus 1, but really it starts at q, because if you plug in q, you get 0. Right? Or in the continuous case, basically, we still have that range between q and q plus 1 that's possible. So we're integrating from q to infinity of x minus q f of x dx. And then, so the cost function has changed from summation to integral, but the result does not really change much, right? We're just, before we had q star was the min q such that probability d less than or equal to q was greater than our critical ratio, right? Now, which was cs minus cp over cs plus ch. Now we have all the possible values of this CDF here are possible. Like everything between 0.1 is possible, so we can get the critical ratio exactly at q star, right? So in continuous case, there is some q such that the probability d less than or equal to q star equals the critical ratio. We're going to have, and that's the same as the CDF, f of q star equals the critical ratio for some q star. And that's going to be exact. The proof of that, like going through this derivation that I showed up top, like basically after I had that cost function, I looked at CDQ plus 1 minus CDQ, right? That's how you can find the minimum of a discrete concave function. For a continuous function, we find continuous concave function, we find the minimum by taking the first derivative, the gradient, and setting it equal to 0. Right? We set the gradient equal to 0. That gives us our extrema, and since it's concave, that's a minimum. And then, like, in order to do that, we'd have to be taking the derivative of the cost function, so derivative of integrals, which uses Leibniz rule, right? So the proof uses Leibniz rule. That's not really necessary to know probabilistic models. And like if you were doing it rigorously, you would also prove that this C function, this cost function, is concave over all Q. And you would do that by taking the second derivative, or the Hessian, right? Showing that it's always positive. The